Thank you for the invitation. So in a small departure from the previous talks in the morning, I would like to tell you about a property that is inherent to quantum error correction that is somewhat surprising. And it's a property about robustness, somewhat in the physics notion of robustness and somewhat in the computer science notion of robustness, property about, complexity, that sort of surprisingly comes out of error correction and sort of interplays this nice connection between computer science and physics. But to do that, we need to sort of start as to why there's a computer science interest in error correction, and there's a computer science error correction from a long line of research. But the big idea in computer science, theoretical computer science, is all about proofs. Classical proofs are described by this class NP, which is the class of all efficiently polynomial time checkable proofs. And you've probably heard of P versus NP. And this class NP, it has these complete problems called constraint satisfaction problems. So it says that, morally, anytime you want to write down a proof, you can always write it down as a solution to this constraint satisfaction problem. And sort of this idea of completeness gives you this nice picture that says, okay, it's really hard to think about all sorts of proofs. It's a very complicated setup. But what I can now think is I can think of proofs as solutions to these kind of constraint satisfaction problems. So a classical proof for a constraint satisfaction problem would just be sort of a sequence of bits, something like this. And then the constraint in the constraint satisfaction problem is a local check. Could be something like take the bit sum of the first 3 bits, and you either satisfy or don't satisfy each of these constraints. And these constraints are, again, they won't be necessarily geometrically local. It's just easier to draw that way. And so together, this generates this sort of proof system where you have this global string, which is your proof, the solution, and it's a bunch of local checks, local constraints that you need to satisfy. Then, given all these local constraints, you can generate a global function that says, hey, what is the value of any assignment? So I put in the assignment and I just check local check by local check what the value is, and it's simply just the addition of terms. And the amazing thing is that it's NP complete, so it encompasses all of proofs to decide if there exists a solution so that this constraint is completely satisfied, Cx equals 0, or if for all solutions at least some term must be violated, that Cx is greater than 1. And this sort of completely canonically, describes the notion of proofs in the classical setting. And this, has been known for many, many years. It starts with Robert Floyd and then Cook and Levin, who sort of understood this notion of non-determinism proofs. This is a very old traditional notion of proofs. Of course, why we're here today is that there's 2 sort of extensions, 2 natural notions of proofs. And the first is the notion of a quantum proof, which is captured in complexity theory by the class QMA. And in a quantum proof, we no longer have discrete bits that describe the solution. It's a quantum state that's entangled across the bits. And so in order to interpret this quantum proof, it necessitates a quantum verifier, which, if you're familiar with complexity theory, means that the verifier belongs to the class BQP. It's a polynomial time quantum device. And just like just like constraint satisfaction problem was this complete canonical problem for NP, there's a complete problem for QMA, and it's calculating the ground energy of a local Hamiltonian system. So it's sort of amazing that this very physics problem of calculating ground energies, this condensed matter problem that's very familiar, is actually complete for this class. It captures the notion of proofs. So really, this is where sort of computer scientists and physicists get to unite, because understanding quantum proofs is equivalent to understanding how to calculate ground energy, right? And also, it gives us a very nice picture as to how to interpret quantum proofs. And for the rest of the talk, we can think of quantum proofs as convincing statements that the ground energy is low or high. If that's all right. Any questions? This is because of this canonical completeness that we have here. And so, just like in the constraint satisfaction problem where you have these local checks, your local Hamiltonian consists of linear local operators, like this one that checks either your all zeros or all ones, and the overall Hamiltonian is the sum of all the local terms, right? And as we know, this Hamiltonian operator gives us a function that takes a state to its energy. Is a very nice, easy function to understand. It's linear on the matrix product state representation. Okay. And the ground energy, yeah, Vedika?
So is this, you need every term HI to be individually satisfied, or do you just want to minimize the overall energy?
We'll just want to minimize the overall energy in a general setting, but morally you can think of it as satisfying all of them. Yeah, so morally think of it that way. There's a little asterisk that one needs to. Yeah, great question. So the ground energy is just the minimum eigenvalue. And you can think of that many different ways. You can think of it as the minimum eigenvalue of this matrix H, which is this 2 to the n by 2 to the n matrix, or you can think of it in this sort of formalism where it's the minimum of this inner product, right? And just like it was NP hard to decide if the constraint satisfaction problem was equal to 0 or bigger than 1, it's QMA hard to decide if the minimum energy is less than A or bigger than B. And there's a gap there. And here there's a small modification from the classical setting. The gap is 1 over poly m, where m is the number of Hamiltonian terms. And that's the setting. And to answer Vedika's question, you can generalize this to bring A to be really, really small, as close to 0, and it's still QMA hard in that setting. But this would be the general version. It's just when there's a gap between it. And, you know, for those who aren't familiar with this notion, if you can solve this decision problem, so this is a 1-bit question. You have to either say it is or it isn't, low energy or high energy. But if you can solve this 1-bit problem, you could use that to perform a binary search to actually calculate the energy. And you can calculate to the precision that was given here. There's one binary search your way down. So for all intents and purposes, if you are thinking about the physics side and say, I want to calculate it, I want a real number, well, this is sort of the thing. You sort of binary search your way till you find the solution, right? So this is a canonical notion of a quantum proof. It's some statement that convinces me the minimum energy is low or small. Okay, but what's a very simple kind of quantum state that would convince you that the energy is low or small? Well, the ground state would be. If I provided the ground state as a state that you could interact with your quantum computer, then what do? You measure the Hamiltonian, you check that its energy was indeed low, and you would be, lo and behold, convinced that it was low energy. So in some sense, what I'm trying to say is that the ground states of local Hamiltonians are sort of canonical notions of quantum proofs. And they capture this quantum class in the same way that we think of proofs for like traveling salesmen or 3-stat or 3-coloring capture the complexity of NP. Right? And so there's a second very exciting reason as to why we should be studying local Hamiltonians in condensed matter physics. Oh, well, I beat myself to it. But there's a second thing that I think one doesn't immediately realize from this is that we widely believe that NP does not equal QMA, that the class of classical nondeterminism and quantum nondeterminism are separated. There's some problems that quantum nondeterminism contains that cannot be solved with classical nondeterminism. But this presumed and widely believed separation yields some unintuitive consequences that are worth mentioning. The first is that the ground states of local Hamiltonians cannot be classically described. That's a very weird statement to start off with, but and I mean this, I should say not all ground states, excuse me. And let me back up and say why, right? So we have this idea that the ground states are canonical proofs, right? But imagine there was sort of an efficient way of describing all ground states. Well then, if you could describe all the ground states in sort of some efficiently checkable manner, then you could also check with a classical computer that they were low energy. So you could solve this canonical QMA problem with just classical computation and it would put it in NP. So the very assumption that NP does not equal QMA necessitates a statement about the complexity of quantum states. It's actually just saying these quantum states are hard to describe. Right? And that's a very powerful statement and something which, if you're a skeptic of NP does not equal QMA, you sort of didn't believe that quantum computers had this power, this would be sort of a location where to target your attack. You'd say, well, I'm going to show that all ground states, do have classical descriptions. And therefore, I would totally be convinced that NP equals QMA and, this whole field is rubbish. But that also leaves a challenge for those of us who do believe that quantum offers some computational advantage, that we have to be able to make statements like this, right? And we have to be able to prove statements like this rigorously. So that's one extension of proofs. That's the quantum extension of proofs from NP to QMA. Yeah,
I had a question is this. So I guess in NP, you are sort of thinking about deterministic classical algorithms. So you could have an intermediate case, which is probabilistic classical algorithms.
That's right.
Can you comment on that briefly?
Sure. There's a class that sits between NP and QMA called MA. It stands for Merlin-Arthur. And it's where the proof is checked by a random classical machine. So it's a machine that gets to flip coins, uses some randomness, but gets to check it. But under what is another classical complexity theory result is that it's widely believed that NP probably equals MA, that this amount of randomization doesn't really help here. So yeah, there is hiding between NP and QMA this class MA, which does capture this. Great question. Any other questions? Yeah, here.
What do you mean by classically describable? Is it just I can write down an equation with a finite number of symbols, or what does it mean?
Right. So that's a fantastic question. So, right, one way to say this is a classical description of this ground state is it's the ground state of H, and then you write down the description of H, right? It's sort of, you could give this tautological description of the solution, but what we will need is some sort of efficiently verifiable. So you need to be able to claim and prove to someone that that was truly the energy. If I give you the quantum state, then you can actually check with your quantum computer that it was indeed low energy. So it's a verifiable solution, right? Because it's verifiable. But if I just tell you that the minimum ground energy of the Hamiltonian is 17, that's not a verifiable statement without, something else. So we'll get into what exactly efficiently verifiable means, but that's a fantastic question. Any others? Okay. So at the same time that this sort of quantum extension for NP was occurring, there was also a different extension that was happening in the classical setting, which was this idea called probabilistically checkable proofs, or PCPs. And to think about PCPs, we have to first think about what we think of as proofs. We think of a proof, and we write a lot of these in our papers, as line-by-line arguments, right? Line 2 follows from line 1, line 3 follows from line 2, et cetera, et cetera. At the end, line 5000 is, the result. But what that means is that if someone needs to check the proof, they have to read incrementally every line and check the validity from the previous ones. Right? It's a very rigorous form, and it's very brittle. Even the smallest mistake causes the whole thing to tumble. Right? That's not an ideal setup for a proof, but is there a proof that's less brittle? One that there could be some errors and some mixtures here and there and things would still work out? And the answer is actually yes, and this was the Pcp theorem. It says every NP problem, morally every proof, you can convert it into a form so that you only need to read order 1 or constant, if the notation isn't clear, bits in order to be 99% confident in the correctness. So no longer can you perfectly convince that the proof is correct. In order to be perfectly convinced, you'd have to read the entirety of the statement. But as you read more and more bits, you exponentially quickly become more and more confident in the correctness of the proof. That's this property of being a Pcp theorem. And another way to see the Pcp theorem is if I told you that it's equivalent to the following statement. It says it's NP hard to decide if there exists a solution to a constraint satisfaction problem, or if all solutions violate half the terms. So if there are m terms in your CSP, if you violate half the terms. So imagine that was the case, that it was hard to distinguish these two situations. I promise you beforehand that it's going to be one of these two cases. And then maybe it starts to become clear how the boxed theorem follows. Because if you're in the first case, you could check every constraint one after another and you'd always see satisfying solutions. But in the second case, you pick a random constraint, right? And you check it, odds are you're going to find a mistake. 50% chance you're going to find a mistake every time. So with one constraint being checked, you're 50% confident in the correctness. 2 constraints check 75, you know, and so forth and so forth, right? It's got this exponential decay because of this property. So this is this PCP theorem. It says that, look, you really could have thought of constraint satisfaction problems in this other light, that it's actually much, much harder to tell. And this is sometimes also called hardness of approximation. It says it's hard to even approximate the solution value of the constraint satisfaction problem. If you're able to even get the first order bits of the value of this constraint satisfaction problem, then there was an alternate algorithm that could have calculated the value of the constraint exactly. And that's sort of amazing, right? But there's an important consequence of this PCP theorem, which is that now we don't exactly need perfect proofs anymore. We don't actually need to read perfect proofs in, but noisy proofs suffice. And what do I mean by that? I mean, take any string x that satisfied most of the checks. So let's say here it satisfies 75% of the checks, right? The value of Cx is m over 4. So it satisfies 75% of the checks. I claim that this string x is also a valid proof, in the sense that you could still read constant number of queries and be convinced with 99% confidence that it was correct or not. And why would that be the case? Well, okay, you pick a random clause, you read it. It might come up true, it might come up false. And after reading one clause, you're not sure because, you know, 25% chance it came up true if it was situation 1, 50% chance it came up true in situation 2. You're not exactly certain. But you read another clause. And now, again, 25-50, 25-50, right? You sort of are trying to figure out, is my coin a biased coin with bias 25-75, or is my coin biased with 50-50 percentage? Well, we know that if I flip a constant number of times, I can actually distinguish those two coins, right? So I still have this property that a noisy proof is still a valid proof. Even if it was a few mistakes were made in the proof, I would still be able to be convinced that the proof was correct, even after reading just a constant number of bits. Is that clear? Was that confusing? Yeah, question? Oh, okay. So the PCP theorem sort of shattered our notion of what a proof is. Our proof previously was this insanely brittle object where every line, every bit mattered exactly. But now you can violate up to 25% of the lines and everything's still all right. You can still verify that the proof was indeed correct, right? And you might say, okay, wow, this is an earth-shattering notion of proofs. What is there a quantum version of this? And this, you know, is the big open question: is does there exist a quantum version of the PCP theorem? Does every quantum proof, can you convert it into a form where you only need to read a constant number of bits to be convinced of its truth or falsehood? Right? You just have this system and you just read, check a few qubits, and you know that the ground energy is low or high. That seems kind of amazing if true, right? And you could write that in this sort of hardness of approximation method, saying it should be QMA hard to decide if there exists a state whose ground energy is, let's say, 0 morally. It could be some tiny a, some tiny constant. Or if all states, the energy is high, some constant fraction. Think of this as like maybe m over 100, m over 1,000, something like this, right? Some constant energy. This question of even, is it hard to understand the first few bits of the ground energy? Like what precision can we learn it to? Sits as the quantum PCP conjecture. And there's some important consequences if the quantum PCP conjecture is true, right? Which is that first, similar to the PCP theorem, it would tell you that every state of energy epsilon over 2 times m is a noisy proof. It's a valid proof, right? For the same exact reason, because if it was noisy, you'd still be able to distinguish it with some good amount of certainty. So as a consequence, the set of proofs in the quantum PCP world is much, much larger than the set of proofs in the non-quantum PCP world, right? Previously, we thought of proofs morally as just ground states. Now proofs are all the low energy states indeed, right? But the fact that the set of proofs is so much larger is going to yield another problem, right? Because we had these two ideas so far. One was that quantum proofs cannot be classically described. We said that earlier. And the second one was what we just said that one slide ago, which is that low energy states of quantum Pcp Hamiltonians are also valid proofs. So as a consequence, if you believe in this quantum Pcp conjecture, you're also believing in this box statement that there must exist local Hamiltonians such that every low energy state cannot be classically described. So not only is the ground state some highly quantum object, but every low energy state is highly quantum. That means there's no product states that are low energy below some threshold. There's no even depth 1 states, no sort of states with matrix product descriptions. All of these things just don't exist. They're truly quantum. They're quantum not only at the solution, but they're even approximately quantum, right? And now we have to come back to one of the statements one of the questions that was given earlier, which is what does it mean to be classically described, right? I previously said, hey, you know, classically described in an efficient manner. Well, that's a really hard thing to sort of pin down. We're not really certain that we have exhausted all the different ways of classically describing quantum states, right? Every week you see new papers that give new efficient classical understandings of quantum phenomenon, right? Which inevitably is saying that there's many, many exotic ways with which we can classically describe quantum information. But let's take one and let's just look at it, which is constant depth quantum circuits. So if you have a state that is the output of a constant depth quantum circuit, so here I'm going to think of my circuits as having, say, 2 local gates and interaction between any of the particles, any of the qubits. And I'm going to think of outputs of constant depth quantum circuits. And I claim that these objects are classically describable and classically checkable. And I'll show a proof of this shortly. But these objects form a classical description just like this. And the combination of these 2 box statements is this previously open conjecture by Friedman and Hastings in 2014 called the no low energy trivial states conjecture, which stated that there must exist local Hamiltonians such that every low energy state requires a high depth quantum circuit to generate it, or the opposite states that no low energy state is the output of a constant depth circuit. So this red box statement is the consequence of the previous 2 statements. This one that says that generically quantum PCPs necessitate a statement of this nature, and the second one is that these constant depth quantum circuits are nice ansatz for classical proofs for quantum systems. And by itself, even if we disregard the whole preamble up to now, this box statement is a very interesting physics statement that is worth considering, because it's sort of describing a robust notion of entanglement that we need to sort of find. And in some sense, what the goal of proving this conjecture is sort of discovering what sort of quantum systems yield this sort of complex, robust entanglement, and whether it even does exist. It's not a priori clear that this should be true or false. And so the rest of my talk is sort of going to be discussion of, hey, how do we prove this statement, and what does it have to do with error correction? So before I continue those slides, can I take any questions? Sorry. Yeah, please.
So I can always think of a state as a linear combination of other states.
Mm-hmm.
Does it sort of trivially follow in some way that this bounds how many linear combination of low depth states I need to get a low energy state? Does that follow in some easy way from this discussion?
Absolutely. So if you had a state that was, the superposition of, let's say, 3 or 4 basis vectors, right, then it would have a nice classical description, and a classical description for which the energy is also efficiently calculatable. It's like a 4 times 4 computation.
It
right?
would also be generatable by a low depth circuit as well?
Not necessarily. Not all superpositions over short basis strings can be generated by low depth circuits.
Okay, so this doesn't necessarily say that some small superposition.
Yeah, that's right. Yeah, so the blue assumption, this ansatz of what is not a complete ansatz in any means, but if we don't know how to prove the black statement, but we do know how to prove the red statement, which is the purpose of this talk.
I'm just trying to get intuition for what set of states that red statement has.
Oh, absolutely. It's unfortunate that the set of states that are describable by constant depth quantum circuits is a tragically small fraction of the classical ansatz, but nonetheless, it's still a first ansatz that we need to lower bound against. Great question. One in the back? Yeah. The dimensionality? Oh. A great question. So, in fact, you can quite simply prove that any Hamiltonian that satisfies the NLTS property cannot live on any constant dimensional lattice. If it was to live on a constant dimensional lattice, then there's a simple cutting argument, you can call it, that would prove that it does not satisfy this. You sort of cut the lattice into regions of size 1 over epsilon, and then you locally solve the regions by themselves. And you could do this with a classical computer in time 2 to the 1 over epsilon. And then, so you'd have a classical solution with a very low energy. Does that make sense? So, yeah, so lattice-based solutions don't work. And in fact, as alluded to by the prior talks, it will necessitate some sort of expansion-based construction, some construction that sits in some higher dimensional setting. Yeah, great. Any other questions? Yeah.
So if we think about just Hamiltonians in 3D or something like that, then we don't necessarily need to be scared about this theorem.
No.
You can say, well, maybe it's
yeah, it's you can sleep easy tonight. Yeah. Right. This is a statement about a very engineered, not a natural system that you're going to see. This is sort of where engineering meets physics, right? Because this is like the intersection of computer science and physics. What we're talking about are engineered objects. These aren't naturally occurring Hamiltonians. But they sort of give a perspective as to if you can engineer this, maybe it does occur somewhere in nature and needs to be searched for. Yeah. Any others?
Yeah, sorry, I have a question. So NLTS, I guess you can rule out, description by a constant depth circuit, but it doesn't rule out, description by a tensor network, for example, right? So what can you say about that? Like, I guess, you have to assume something like QCMA is not equal to QMA, which I guess you can explain to those people who don't know. But I guess if you assume something like that, can you also rule out like no low energy, like tensor network states or something like that?
Yeah, so if you made an assumption on the order of like QCMA does not equal QMA, it would say something like the solutions to ground states cannot even be described with polynomial bits in a way that a quantum computer could interpret them. Right? It's a very powerful statement, QCMA not equal to QMA is. So yeah, if you assume something that big, those kind of statements are easier to make. But we want to start with a more reasonable assumption like NP not equal to QMA. And NP not equal to QMA is the precursor as to why this problem is interesting. But the solution to this problem is not based on any complexity theoretic assumptions. It's a full-on proof that no low energy state is the output of a constant depth circuit.
A question and a clarification. So the question is, do you care about pure versus mixed states?
No.
Okay. And then by low energy, you really mean low energy density, right? So we're talking about finite but low temperature states?
Yes. So energy below like a constant fraction of the total. Yeah. Great. Okay. So here sits the theorem, and as we sort of previously said, it's going to follow as this consequence of the quantum PCP conjecture. So it was a good place to start if you were a disbeliever. If you broke this, then you broke quantum PCP, and it would really change, our understanding. But as I said, also it's making a statement about physically realizable robust entanglement. And so the result of my paper earlier this summer with Anurag and Nico was that local Hamiltonians that correspond to most, I'll say with an asterisk, linear rate and distance quantum LDPC codes are NLTS Hamiltonians. That error correction sort of is a way of proving that these Hamiltonians with these robust properties exist. And, you know, a priori, I think this is a little surprising. When I told my advisor, Umesh, about this, Umesh thought this was sort of strange because, you know, error correction, as Victor described, was really designed, so to speak, to correct single qubit errors, right? The assumption was that when the noise model propagates, it's a, you know, collection of some constant number of qubits have an error. It's not some like global error that affects all the states. But what happens here is that the low energy spectrum doesn't necessarily just contain these sort of small errors on a constant number of qubits. It also contains these weird errors that are like rotational shifts in the Hilbert space in like the high dimensional block sphere. You know, you just take the state and you move it by a small angle. It contains linear combinations of errors. It contains all sorts of messy things. And yet error correction, which was designed to correct, you know, discrete errors, has this kind of continuous property to it. And that's sort of the more physics interesting statement I think that this theorem provides. So another reason why to consider studying error correction more deeply is that it's not just about discrete errors. It's actually saying something more about continuous errors than we previously suspected. So the formal statement I'll prove is the statement in blue that, you know, every state of energy less than epsilon n, and as Vedika asked, it's any mixed state of energy less than epsilon n, the minimum circuit depth required to generate psi is going to scale as log n. So constant depth, the lower bound is actually logarithmic, not just constant. Yeah. Okay, 3 parts of how this proof go. One is I'm going to sort of explain how trivial states, those are states that are the outputs of constant depth circuits, are correlated with local Hamiltonians and circuit depth lower bounds. The second thing is I'm going to have to just remind some ideas from error correction, classical error correction actually. And third is I'm just going to note a little bit about how erasure errors work in the quantum setting. And, you know, as soon as I sort of finish these 3 points, the proof will just fall apart in seconds. Oh, sorry, come together in seconds, not fall apart. Other way, yeah. Come together in seconds. Okay. So let me talk about light cones. So if you have a local operator in a quantum circuit U of constant depth, then you could think of the operator that is A sandwiched between U. So I just think of this as sort of the operator A in the rotated basis that the unitary U describes. And if I thought of this as a physical operator, I could say, hey, look, the operator A, I put it between these 2 circuits here. But I just think, what's going on with these circuits? Can I simplify this description of U, A, U dagger? And the answer is yes, because if there was a gate out here outside of this sort of light cone region in the circuit, right, this gate just cancels off with its neighbor on the other side. So what I get is that UAU dagger simplifies as a computation just by this cancellation into an operator that acts on at most 2 to the t times a qubits, right? That like this description, which was kind of this big description initially, now actually sandwiches down to become something very simple. Sorry, question?
We're talking about 1D circuits with only local connectivity or something?
No, we're talking about all-to-all connectivity. I just draw it this way for simplicity. So the light cone at each level doubles in size. So that's why with a depth T circuit, the light cone scales as like 2 to the T. Yeah. But if you wanted to talk about the same object can also be considered in constant depth, constant dimensional circuits, and then the light cone scale as like linear in T, right? Great question. And here's the first thing that we need to say, which is why were constant depth quantum circuits a classical proof? And here's why. If you're given a local Hamiltonian and a state psi that was the output of a low depth circuit, my claim is that you can evaluate the energy exactly in time 2 to the 2 to the t. Okay? And here's how. So this is, if I can do this, then I have proved to you that these constant depth states are, you know, classical proofs, because if you did this, 2 to the 2 to the t is a constant now for, you know, and so then I have a constant time classical algorithm for calculating the energy. So the idea is simple. The energy is just the linear combination of the local energies, But now I get this fact that psi is 0 times u, right? So now I have u dagger h by u. But this guy is a computation only on 2 to the t qubits. So I can brute force a computation on 2 to the t qubits in 2 to the 2 to the t time, which is exactly what I wrote here, and so I'm done with my proof. So my low depth states are classical witnesses for energy. So at least this should be convincing that we need to lower bound against these very simple objects because they are the easiest sort of classical witnesses I need to consider. Okay, now I'm going to make a simple fact that I'm not sure everyone here is familiar with, which is that trivial states, states of the outputs of constant depth circuits, have a very nice corresponding local Hamiltonian always. So if I take the state 0, it's the unique solution to a very simple local Hamiltonian, and that's the Hamiltonian H0, which is just single qubit projectors onto each of the particles that just make sure that it's sitting in the 0 state. It just projects against the 1 state, right? And this Hamiltonian, because of its simplicity, is really easy to analyze. It's commuting. It has a very simple spectrum. Its spectrum are just integers. And the eigenvalues are, for any eigenvector, just correspond to Hamming weight, right? But now what I can do is I can say, hey, let me take this Hamiltonian, let me rotate it. If I rotate the Hamiltonian by the unitary u, and I call this hu, right? Then I get the same statement about the spectrum and commutation, because I'm just rotating by a unitary. But the eigenvectors are now u times x, right? Because that's just simply the rotation of h0. And what that means is that there is a unique eigenvector of eigenvalue 0, right? Because h0 had a unique eigenvector of 0, which was just 0. So u applied to the 0 state is a unique eigenvector, and that this Hamiltonian corresponds to it. But from the argument that we made in the previous slide, hu is now a 2 to the t local Hamiltonian, right? Because it's u dagger hu for each local term h, so that gives you a 2 to the t local thing. So we have a local Hamiltonian whose unique eigenstate is exactly the state that we want to understand. And so it's a very simple Hamiltonian, and this is sort of a proof technique that will be very useful over the rest of the talk. Okay, so just given what's written here on trivial states of local Hamiltonians, I actually claim that we can prove our first circuit depth lower bound. So, right, the name of the game is to sort of prove that states have high circuit complexity. So, in some sense, that's proving lower bounds on the circuit complexity. And I claim that just what we've written on this slide is enough to start proving circuit depth lower bounds. And what I'll show is that if you have two states that satisfy this property called local indistinguishability, that you can immediately prove circuit depth lower bounds for these states. So we say that two states are locally indistinguishable, or d-locally indistinguishable, if for every region, every collection of qubits of size less than d, the reduced density matrix on everything on those d qubits are identical. So that means that if I look at the regions, I just picked the d qubits from the first guy and the d qubits from the second guy, I cannot tell those reduced density matrices apart, and that's true for all regions of size d. If I have this property, then I call these states d-locally indistinguishable. There's a very nice example of d-locally indistinguishable states, and those are the cat states. The cat states with the positive and negative sign, these two states, they're orthogonal, but they're locally indistinguishable for any n-1 qubits. If you take any n-1 qubits of the cat states, the reduced density matrix loses that global phase. So the global phase is only revealed if you have all of the qubits. Any fewer than that, and there's no global phase, and these states are indistinguishable. So first things first is we can prove a lower bound as to the complexity of cat states. And here's how we're going to do that. So here's my lemma. If you have d-locally indistinguishable states, and you had that one of the states was the output of a circuit U of depth t, then t must be greater than log d. Okay? So how am I going to prove this? I'm going to prove it by contradiction. So let's assume that it's false. Let's assume t is less than log d. Okay? Now what I'm going to do is I'm going to consider what happens when I take psi prime, the other state, and I consider its energy with hu, which was this Hamiltonian built for psi, right? Well, I'm going to get that its energy is the sum of these local terms, but the energy of psi prime on H should be exactly the energy of psi on HI, right? Why is this the case? Well, it's because HU is 2 to the t local, right? It's a local thing, but these are d which is greater than 2 to the t, locally indistinguishable. So this local operator cannot distinguish the two states, so its energy with the two states must be the same. But that's just the energy of psi with H, sorry, that should be HU right there. Psi with HU, which is 0. Well, what does that tell you? It tells you that psi prime is also a state of energy 0. But like we said previously, HU has one unique eigenvector of eigenvalue 0, which is just psi, so therefore psi equals psi prime, which is our contradiction. So immediately, local indistinguishability is sort of a technique for proving circuit depth lower bounds. And in some sense, local indistinguishability is sort of the quantum property that is being captured by these log depth circuit lower bounds, which is that if you can find these sort of locally indistinguishable objects, you're proving these lower bounds. And so in some sense, the proof of NLTS, at least the path that the three of us took, was about robustly showing that ground states were locally indistinguishable. Okay. Now, this argument, though, it's a little lacking, don't you think? Because what happens here is that this required that psi and psi prime were locally indistinguishable exactly, that the reduced density matrices were exactly the same. It doesn't really say something about what the complexity is of states that are near psi. Ideally, I'd want to say that because of this argument, not only is psi complex, but any state that's in a small perturbation around psi is also complex, right? Does that make sense? But that doesn't really come out of this, and the reason it doesn't come out is because the spectral gap of this Hamiltonian was just 1. So what this did was this argument had some robustness to it, because this argument really tailored on this unique ground state requirement, right? That's where the contradiction came through. But you could sort of nudge that a little bit as long as you had two states which were at high enough overlap. But because the spectral gap was so low, you couldn't really make that argument too robust. So this argument is only robust to perturbations of the order 1 over n. What that means is that if you took the state psi and psi prime, and you perturb them just by a little bit, 1 over n, then you'd still be able to prove the lower bounds, but that's not really what we want. We want constant perturbations, right? Because we're looking at the constant error regime for the noise. But you can actually make this a little bit more robust. You can use some mathematics from Chebyshev polynomials and make it robust. And so here's sort of the robust statement that we can show, and this is sort of a generalization of the cat state lower bound that I previously said. So it said let S1 and S2 be some sort of subsets and P a probability distribution. Then if the probability distribution has some mass on two regions, then the minimum quantum circuit degenerated as this complex thing. I'll show you a picture. How about that? Instead of this kind of garbage statement. So it says, let me draw out all of 0, 1 to the n, and let me think of S1 as some set. It doesn't have to be a continuous set in the block sphere. It could be some like union of disjoint regions, and you have some S2. And now if you imagine a probability distribution over this Boolean hypercube, as long as the probability distribution granted mu mass to S1 and to S2, then you can prove that the circuit lower bound scales as log of the distance between the regions. So this is the Hamming distance between the regions squared times mu over n. So as long as these regions are further than square root n from each other, you're able to prove non-trivial circuit lower bounds. Sorry, do I have till 12:30 or till 12:15? 12:15. Oh, okay. Okay. Yeah. I think you can go like 5 or. Okay, great. How much do you think? I'll intermix the questions. How about that? Okay. So, and so this statement is sort of the robust version of the lower bound for the cat state. The cat state is sort of a distribution which has two masses, one on 0 to the end and one on 1 to the end on corners of this Boolean hypercube. But this says I can generalize that the masses don't need to be fixed on one specific point. They can sort of be on regions as long as the regions are far apart. And the masses don't have to be 50-50 either. They can just be some constant. And the way you sort of prove this is you show that there exists, if you did have some state psi which generated this probability distribution, by that I mean that if you measured psi, it would induce the probability distribution P. So if you had such a state psi, then you could always find a region R, so that if you took psi prime, which is you sort of flip the sign of psi on all of R, then these states psi and psi prime are approximately locally indistinguishable. That the Hamiltonian cannot distinguish these two states, the Hamiltonian being HU, where U is the circuit generating psi, and therefore, you hit the same kind of contradictions. So we sort of see that local indistinguishability plus some Chebyshev polynomials gives us this robust lower bound here. Okay, so yeah, so when the distance is super quadratic and mu is a constant, this is a distribution which we call well spread, and this is a distribution which is sort of great for proving lower bounds, right? Because if we have these sort of well spread distributions, they're sort of robust, right? Small perturbations in the distribution still remain well spread. So what I get is that I can continue to prove circuit lower bounds by this consequence. So what I need to do in order to prove the NLTS is I need to show there exists a local Hamiltonian whose entire low energy space induces well spread distributions. And for that, I'm going to use error correction. Yeah.
When you say well spread, does that require from any pair S1, S2?
No, just the existence of it. Yeah. Okay, so where do well spread distributions come from? Well, here's an idea. They come from error correction is one great place to find them. So linear codes, as we previously discussed, can be kernels of matrices H. And what you can get is that if the check matrices of these codes are expanding, as sort of suggested by Eugene, then what you get is that sort of the following picture. You get that the code vertices sort of are far apart like this, but the states that violate an epsilon fraction of the terms sort of cluster in regions around the code words. You get that if you violate a few checks, the strings that violate a few terms look like this. But this isn't actually the entire picture. You actually get that there are these kind of phantom regions that occur where these words also violate an epsilon fraction of checks, but they're totally far away from the original code words. These phantom regions don't necessarily have to be anywhere close to codes. But the property of expansion actually tells you that that's okay. These phantom regions still are order n from all the other regions and all the phantom regions themselves. So you sort of get this clustering property that the low energy space looks like this clustered picture. Okay, let's not worry about the proof of that. So the low energy space of a classical code seems like the great support for a well spread distribution. And you might ask, hey, why don't you just pick a classical code as your Hamiltonian for proving NLTS? Well, that would tell you that all the low energy states are supported on these green clustered regions, but it doesn't preclude the fact that the distribution could be concentrated on any one vertex, or in particular could be concentrated on any one cluster. In order to prove well spreadness, we need to show that the distribution isn't concentrated on any one cluster. We need to show that it has mass on all these clusters. And just having a Hamiltonian that is classical will not prevent that issue. So what do we need? We need sort of a Hamiltonian that's in two different bases at the same time, and that's where these codes come in. So that's where the quantum codes, really give us everything we need. Mm-hmm.
What types of classical codes do you use for?
Just random codes even. Yeah. Random codes have this property, this kind of clustering thing. Because random codes are small set expanding with high probability, so most codes give you this. Yeah. Great. So we want to construct Hamiltonians with such property, and where are we going to look? We're going to look at quantum error correction. Now, in the previous talks, we thought of quantum error correction as correcting Pauli errors. But if you can correct Pauli errors on a few qubits, then you can also correct linear combinations of Pauli errors on a few qubits, which means you have to be able to correct erasure errors. Which means that if I had a state like this yellow region with this blue region highlighted, and the blue region was to be removed, then there exists a recovery map from which I can recover the state as is. But what that tells me is if I kept the blue region along, that that blue region cannot have any information about the original state. Because if it did have any information about the original state, this would violate the no cloning theorem, right? Because you'd be able to make a partial clone. So that blue region was completely independent of what state was encoded in the error correcting code. So as a consequence, actually, quantum error correcting codes have local indistinguishability almost immediately. And NKD code is D-locally indistinguishable, which is, why we use that letter there. And so exact code words of distance D codes require circuits of depth log D. So we should be looking at codes with distance that scales polynomially. Okay, that's great. And error correcting codes have a natural Hamiltonian. There's just, you have one Hamiltonian term for every check in the code. So now we're really cooking, we're getting somewhere. And so we now just need to prove circuit depth lower bounds for the low energy subspace of sort of these code Hamiltonians. Okay? And so what we need is exactly CSS codes. And we're going to need optimal parameter CSS codes. So now the CSS codes have a picture that looks very similar to the picture for the classical code, except for the fact that if I sort of project the CSS code onto the Boolean hypercube, so I take the classical projection, then I get that the code words of CZ sort of form these sort of small clusters themselves in regions like this, and that the distance, the Z distance, is the distance between these clusters this way, and there's an analogous X picture, right? I don't need to draw both pictures because they're just analogs of one another. And if we have sort of an expanding notion of CSS codes, which was which actually turns out to be true in all the constructions we've seen so far of these optimal parameter CSS codes. So this construction sort of gives me this sort of region. Sorry, there's like a small highlighter region. I don't think it shows up too well on the screen today. But what I get is that the low energy space around these codes sort of forms the same sort of clusters, just like we saw in the classical picture. So if I have this property that these codes satisfy sort of a small set expansion similar to the classical small set expansion, then I get this sort of clustering property all on its own. And I should think of this more as like an extension of the notion of distance, a small robustification of the notion of distance. And Sunny He, who's a student at MIT, told me that he thinks that this robustification of distance is actually what is like at the heart of giving the quantum error correcting codes their decoding properties. So I don't know that for sure myself, but I think it's worth studying that this robust notion of distance is really where decoding is coming from. But now we sort of have a quantum picture of these codes, and now let's just see how everything finishes up. So what you get is that if you take a low energy state, let's say epsilon over 200 fraction low energy state, and you measure in the Z basis, if you have a code that satisfies this sort of property here, this sort of clustering property, what you get is that it's going to be, the classical distribution you yield is going to be 99.5 supported on these clusters. Okay, so we have the support, now we just need to show that it's not concentrated on any one cluster. If we have that, we have well spreadness for distribution. And to do that, we're going to need something that's little quantum, right? So far, nothing I've said is quantum yet. We've only done classical things. And we're going to use the uncertainty principle. So I may not be able to show that this picture is going to be clustered in the Z perspective. So I may not be able to prove that if I measure in the Z basis, I'm going to get a well-spread distribution. But what I can show is that either in the X basis measurement or the Z basis measurement, I'm going to induce a well-spread distribution. And that's enough to prove the lower bound because it proves that it's well spread somehow. Right? So how do we do that? So we want to prove that there's sort of some clustering into two halves. And all that really remains to show is that it's not too concentrated on one cluster. So the uncertainty principle, there's many different ways to say it, but here's one, which is that for any two sets S and T, if your state has a lot of mass when measuring the Z basis on S, then the amount of mass it has on T is kind of small, and the amount it falls off with is sort of the inner product of the size of S and T. Okay, so what we're going to show is we're going to show that, look, you can't be concentrated in both the z basis and x basis on clusters. And that's pretty simple to show. So how do you do that? You say, well, assume it was concentrated in the z basis on some z cluster. Then we want to show that for any x cluster, it's not concentrated. Pretty simple. And all that requires is taking this uncertainty principle and plugging in the values. So the size of these clusters is pretty easy to calculate. It's bounded by 2 to the rate of the x code plus orders that scales with epsilon and n. And that's because there's sort of the cluster is defined by the quantumness of the code, which is this CX perp region. And then there's this spread due to the low energy system. And similarly, there's a bound on the X cluster. And so you just put these kind of bounds together, little algebra, but here's the weird part, is you're going to get the rate of the code pops in. And this is probably the part that confuses me the most, is why on earth the rate pops into this equation. But it says that unless the rate is good, then you can't necessarily prove this this well-spreadness in either basis, one or the other. So we're not exactly certain if this is necessary or just an artifact of the proof, but this is definitely necessary. So it says that if the energy epsilon was smaller than the relative rate squared, then you get this sort of clustering property. So you get that the distribution is well spread in either the x or z basis as long as the energy is less than the relative rate of the code squared. With that, you sort of have the whole proof together. What we needed was the quantum code to sort of simultaneously get this uncertainty. So we had our distribution was spread, and we needed the classical code ideas to sort of argue that the distribution was sort of clustered on these far apart regions. And that allowed us to prove lower bounds as to the complexity and therefore show that these objects, these Hamiltonians, the solutions are truly quantum from the very beginning. So the conclusion is says that these CSS codes of linear rate and linear distance, which expand, are they're NLTS. They have this complex entanglement, or that any state that violates epsilon fraction of the checks cannot be the output of a constant depth circuit. Maybe I should end by just saying, what does this say about quantum PCP? Well, I'm not sure it says anything about the positivity of quantum PCP. It says something. It doesn't necessarily say that the quantum PCP is likely true. Maybe it says that the quantum PCP is likely not false. Does that make sense? So it's not as, it's saying that this one simple way of disproving the quantum PCP seems to be false, but maybe there are other classical ansatz that we need to understand, which sort of explain classical proofs of local Hamiltonians. So that's something I am actively exploring at the moment. And with that, I'll end with any other final questions. So. Yeah? Yeah, in the white shirt? Yeah.
So I was wondering whether there have been some results on the complexity of random quantum circuits that random circuits cannot be compressed into shorter one.
Mm-hmm.
So what's actually the trick of taking your local Hamiltonian and conjugating with the unitaries? I was wondering if you. Okay, so maybe I will repeat. So I was wondering whether you can use some of the recent results on the complexity of random quantum circuits, as they show that certain random quantum circuits cannot be compressed into short ones. So going back to your local Hamiltonian that you conjugate with some unitaries, if you conjugate that with random quantum circuits, whether you could imagine that a proof goes in the way of saying, you're conjugated with a random theory, therefore you cannot compress them, and so this gives you some local Hamiltonians. First, say eigenstates cannot be compressed into shorter quantum circuits.
I see. So you're saying that all of these states could never be compressed?
No, well, of course, because then, they cannot be compressed with certain exponentially, up to some exponentially small probability. So the idea would be that you collect the first m eigenstates, and then maybe you can play with the, competitions of how many eigenstates you collect, and because they prove that, for certain random circuits, you pick some product state, you have always some random circuits, and then with probability 1, you cannot compress this into shorter ones. Mm-hmm. And so really by picking your local Hamiltonian, I conjugate with that, and then I might be able to say something.
That would be very interesting. My suspicion, though, is that these lower bounds are against all states of low energy and all circuits that generate them. So any argument that says with high probability sort of fails at that line, because these ideas come from like adversarial proofs. It isn't just lower bound sort of the low energy states that form from like natural errors. It's also lower bounding some sort of adversarial low energy states that could be provided. So. Yeah, with the mic.
Yeah, thanks for the very nice talk. So I was wondering, do you have any intuition whether the linear distance is essential for this property?
Right, so the linear distance does seem to actually be essential. In fact, the sort of this expanding notion, we need this sort of stronger version of linear distance, that even if you make small errors, you don't move too far from the space. And so, yeah, both linear distance and linear rate seemed essential to the argument, which was somewhat surprising. I had always thought that linear distance was maybe not necessarily, that even like quadratic distance could be NLTS, and that hasn't been disproven, by the way. So even like the hypergraph product codes could be NLTS. We just don't have clean proofs of that yet, or disproofs. Yeah. There were some more questions back.
Yeah. So one property related to PCP is that it's hard to approximate the free energy at a low temperature because the free energy is E minus TS, and when the temperature is small enough, the entropy term will be negligible. So that's just to motivate the question. The question is, for these codes, can you say anything about the thermodynamics, either in or more interestingly out of equilibrium when the temperature becomes small?
I can't personally. I hope someone else can. Sorry. No, I'm not sure. Yeah.
Hey, thanks for the talk. I had just kind of a conceptual question. Originally, when you discussed the NLTS conjecture, I think one of the motivations was that like low energy states of certain Hamiltonians you can think of as noisy proofs for statements that are hard to show. And so there are probably, those states are probably not classically representable. But I guess the states that you ended up talking about for these LDPC codes are classically representable, but they can't be generated, you're saying, within a finite energy window by a finite depth circuit. So do they not correspond to proofs of hard statements, or what's the connection there?
Yeah, so I mean, these Hamiltonians are stabilizers, so they have this other description through this Clifford formalism that really simplifies. This is sort of saying that this one classical ansatz, constant depth quantum circuits, is not a reasonable ansatz that disproves that ansatz doesn't disprove quantum PCP, right? Maybe the Clifford ansatz disproves quantum PCP. Maybe some combination of these ansatzes is what disproves quantum PCP. All that remains to be verified, right? And in some sense, you could say that it also proves a rigorous statement that the classical ansatz given by Clifford formalism and the classical ansatz given by constant depth quantum circuits are like apples to oranges, even in an approximate sense. They're not sort of comparable. And this is an example for which they are very easily describable with Clifford formalism, but bad at being described by constant depth formalism, right? Even approximately. And maybe the other way is also true. I think that's easier to show. So, yeah. Any other questions? There was one over here. Okay, great.
I had one, which is, so you showed that low depth states with the low depth circuit representation are classically easy to calculate the expectation values of your Hamiltonian, but such states could still be sort of complex or not for other tasks, like sampling output distributions.
That's right.
And then your proof actually used things about output distributions. So does it somehow say that those ground states are also complex from that perspective?
No, so the sampling task is about correlations between all the bits that are being outputted, and constant depth quantum circuits can provide provable quantum advantage over classical circuits in that regime. Here, the fact is that the energy is measured through this local phenomenon, right? The energy is measured by a local Hamiltonian. So since it's the linear combination of all these energies, there's not some global test being administered as to the output, which is why these constant depth circuits are low energy. But for sampling, which is a fundamentally different question, or even relation questions, these constant depth quantum circuits are still fundamentally interesting, just not in the decision Hamiltonian regime. Does that make sense?
Thanks.
Great question. Yeah, Vedika?
So you know the energy density that you were talking about, you had an expression for that, which had the code rate in there.
Yeah.
So certainly if you want a finite energy density, you need a finite code rate.
Yeah.
But is there some function of the distance and the rate which says that, you know, for energy less than this function, we need a depth, which is at least some other function, which, you know, it may not give you exactly as good of this NLTS conjecture, but it'll give you some partial statement of complexity.
Yeah. So the rate of the distance, the relative d over n and the k over n, those constants do appear in what is like an upper bound as to what that epsilon could be. Yeah. I just don't know what those are, and it's sort of superfluous, right?
So they appear in both epsilon and the circuit depth that you need.
Yeah. Yes?
If I get access to interaction instead of just a single proof, does that change the story significantly, or is it still true that interactively I can't get some sort of
With classical interaction? So quantum proofs have this, so this idea of proofs with interaction has been studied quite a bit, and there's a class called IP, which was captured the complexity of this and was shown to equal P space. All the problems that could be solved by just a computer that gets to run with a polynomial space bound. And you can show that quantum interaction is actually not any more powerful. It's still exactly equal to P space. But what you do get as an advantage is a round complexity advantage. At quantum proofs, you only require 3 rounds of interaction, whereas classical proofs may require polynomial and n rounds of interaction, where n is the size of the question being asked. So what that means for PCPs is not immediately clear to me at the moment, but we can chat afterwards, perhaps.
All right, I don't see any more immediate questions, and I believe there is lunch waiting, so let's thank Chinmay once more, and then